Ecological System Algorithm (ESA), developed in 2012 by Abdelrazak Merab. ESA is a bioinspired search algorithm that imitates the ecological equilibrium between species to optimize a given function. ESA searches for solutions to a given problem by choosing random candidate solutions which are evaluated using a fitness function. If the proposed values give high fitness value, they are taken into consideration. ESA uses two individual groups in its search, a herbivorous and a carnivorous group, and simulates the motion of real animals in nature. The herbivorous group benefits from high fitness values of the optimized function, and the carnivorous group travels across the environment looking for prey. ESA is a swarm intelligence algorithm where individuals have naive actions that require no calculation or reasoning to solve. Despite the naive behavior of each individual, the overall behavior of the algorithm can be described as intelligent. ESA will be used to tune the PD controller of a quadrotor. The PD controller is a closed-loop controller that controls here the height, the roll, the pitch, and the yaw of a quadrotor. Each of these variables will have its own controller, PD controller. The first PD controller is the one controlling the height or the altitude of the quadrotor. The second one is the controller that controls the roll or the phi angle, which is the rotation around the x-axis. The third controller is the one controlling the pitch angle or the theta angle, the angle around the y-axis. And the final controller is controlling the yaw angle or the psi angle, which is the rotation around the z-axis. Now for each variable, the search space is a 2D plane with proportional gains as x-axis and derivative gains as y-axis. We will have 4 different search spaces, one for each control variable. To tune the PD controller of the quadrotor, ESA starts by generating random gain values as initial search elements. These are the zebra species for each control variable. The gain values are increased or decreased randomly to simulate the zebra individual's movement inside the search space. Here, for example, only the height search space is shown. It is a 2-dimensional search space with the x-axis giving the P gains, the proportional controller gains, and the y-axis giving the differential controller gains. The first step in ESA is to generate the search variables, which are points spread randomly in this search space. Each point has an x coordinate, which is the P gain, the P controller gain, and a y coordinate, which is the differential controller gain. Here, for example, for the height controller or altitude controller. Now, each set of the height gains is evaluated, so it is used to control the quadrotor. The height response of the quadrotor is found, and the sum of errors of this gain set is calculated. The fitness value of each gain set is equal to 1 over the sum of errors of this gain set, or the reciprocal of the sum of errors. Sure, this is done for each search variable, but here we are showing only the height variable. Now, according to ESA, a random step should be made. This is made by adding a random value, whether it is positive or negative, to the gain sets. Thus, new gain values are calculated from the old gain values. Now, these new gain values are evaluated, so they are used to control the quadrotor, and the quadrotor response is found, and then the error is calculated for each set of gains, and finally the fitness value for each set of gains is calculated. Next, the health values of each gain set is updated. Now the fitness values, the old and the new fitness values are compared. If the new fitness value is more than the old fitness value, the health is increased, else the health is decreased. Now, gain sets that had their health values increased give birth or generate new gain sets at the same location. Now, a search element or gain set dies if its health falls below a given threshold, or it reaches the maximum iteration life. Now the above steps are repeated iteratively until all gain sets giving low fitness value are perished, and all the remaining gain sets are gathered at the locations that give the maximum fitness values. Thus, the best values for the gains, the PD controller gains, are found. This search is applied for all the search spaces at the same time. So the optimal gain values of all controllers are found with only one search. Now, introducing a predator species fastens the search and allows to discover new regions. Gain sets, which are prey sets, and predator sets are created. Each set has a health and a maximum iteration life. Predator elements attack close gain sets and help exterminating weak gain sets quickly. Predators that manage to eat in an iteration increase their health values and breed a new baby predator at their locations. In a confrontation between a predator and a prey, health values of each element are compared. If the predator health is more, it manages to eat the prey. Else, the prey manages to escape, but with some injuries, so its health is also decreased. After many iterations, the algorithm will find the optimal gain value quickly and with no local minima. Finally, an ecological equilibrium will be set. The optimal gain values of all controllers are found using predator-prey search (ESA) algorithm with only one search. Here we can see the naive actions of a zebra or prey. Move randomly and increase your age at each step. Calculate the fitness value in old and new locations. If the fitness value is more in the new location, increase the health, else decrease the health, and breed a new baby whenever you move to a new location. Repeat these steps until your age is 10. Here I'm assuming that the iteration life is only 10. And whenever attacked, compare your health with the health of the predator. If your health is better, you manage to escape, but decrease your health. Else, you will be eaten and die. Here we can see the naive actions of a predator or a lion. Move randomly and increase your age at each step. If your age is 10 iterations, so you die. If you find any close prey, attack it. So compare your health with the health of the prey. If your health is better, is more, eat the prey and increase your health. Else, the prey will escape and your health will be decreased. If your health is less than a given threshold, you will die. Here you can see the interaction between the predator and the prey species. Both species will interact with each other until a termination criteria is met. I used the ESA to tune different types of controllers for quadrotors and octorotors, and many publications rely on ESA. For example, we have 2 book chapters, 3 journal papers, in addition to 8 conference papers. This video is originally prepared in 2016, but the voice is added and slight changes were made in 2024. Thank you for watching.